Okay, so we start with mechanics of solid. As I told you, elasticity म्हणजे एखादी body elastic म्हणजे त्याचा अर्थ काय होतो? It basically means if you apply force, the shape of the body will change. That means it will undergo deformation. फोर्स काढल्यावर जो जर ओरिजिनल शेपमध्ये आला तर अशा बॉडीला आपण इलास्टिक बॉडी म्हणतो. सो इफ ए बॉडी इज एबल टू रिगेन इट्स ओरिजिनल शेप ऑन द रिमूवेबल ऑफ डिफॉर्मेशन फोर्स, इट इज सेट टू बी इलास्टिक बॉडी. आणि तसं जर घडलं नाही, इफ एखादा बॉडीवर फोर्स अप्लाय केल्यावर त्याची पूर्ण शेप पूर्ण रिटेन झाली नाही, थोडीफार डिफॉर्मेशन त्यामध्ये राहिलं, तर दॅट टाईप ऑफ बॉडी इज कॉल्ड प्लास्टिक बॉडी. तिसरी परिस्थिती अशी आहे की एखादी बॉडीवर फोर्स अप्लायवर केल्यावर तो तुटून गेला, म्हणजे उदाहरणार्थ ग्लास. सो इफ यू अप्लाय फोर्स ऑन इट, इट विल ब्रेक. करेक्ट. सच अ बॉडी इज कॉल्ड ब्रिटल.
Yes, sir.
Actual practice, there is no body which is completely elastic or completely plastic or completely brittle. There is a limit to which this can exist. Correct. That is called the
तुम्ही
limit
screen
of
share केली.
elasticity. Hello.
तुम्ही screen share केली.
Hello.
Yes, sir.
Yeah. Can you see the screen now?
Yes, sir.
Yeah. So basically going back again, so you know what is mechanics of solid, correct? बेसिकली आपण इथे सॉलिड बद्दल बोलतोय. सॉलिडचा एक प्रायमरी प्रॉपर्टी इज दॅट इट हॅज अ सर्टन शेप. दॅट मीन्स the molecules within the body are at a particular position, which is the equilibrium position. In this equilibrium position, the particles have got optimum minimum potential energy and the net force is 0. So if you change the position, correct, then the intermolecular forces interact in such a way that it tries to retain the original position of the molecule. This is what happens inside the substance. On the external side, we can see that on application of a force, the molecules are shifted, so the body loses its original shape. But the moment you remove the force, it comes back to its original shape. Such a body is called elastic body. In case all the particles are not coming back to their original shape and a certain amount of change in shape does exist in spite of the removal of the force, then it is said to be plastic. And if a body completely disintegrates, means the molecules separate from each other, they are no longer held with each other, or they break up, such a body is called brittle. Correct?
Yes, sir.
Now deformation is in simple terms can be said as change in shape. So if a body changes its shape, then we say it is deformed. And any force that brings about such a deformation is said to be deforming force. Okay? Is it clear? Hello?
Yes.
Yeah. Now we go further. Now to quantify them or to study them in actual practice, what we do over here is we define certain things. We call stress as the deforming force upon the area. And we define strain as the change in dimension of the body to its original dimension. Okay. Now if you look at it in the sense that what exactly is stress, okay. So for that matter, let us say that we have a body which is originally like this, correct? So originally it is this way and we are applying a force at this end, correct? If we apply a force like this, what will happen to the body? Tell me. It will elongate, correct?
Yes, sir.
Okay. So this is the external force that we are applying. So when you apply this force, this body which was originally at this place, it will change, correct? It will undergo a change, it will become like this, correct? So this particular thing is the change in shape that we have produced. Now because of this, what happens is, because of the external force, there is internal force that are generated within the substance, and these forces try to regain the original shape. Okay, this try to regain the original shape, and this force is exactly equal to the applied force. So if you remove the original force, the body will come back to its original shape. Now notice carefully that the force is not acting at a point, but the force is applied across the surface on which you had applied the external force, correct?
हाँ.
So instead of talking only in terms of force, we call it as stress, which is force upon area. Is this clear to you?
Yes, sir.
Okay. So this is force upon area. So its unit will be Newton per meter square. Newton per meter square. Okay. Is it clear? It will be Newton
Yes,
per
sir.
meter square. Okay. Coming back to strain, look back at this thing. So let us say that the original length of the body, हा जो आहे इथून इथे, this was the original length of the body, correct?
हाँ.
So this was the original length of the body. So let us name it as capital L. So capital L was the original length of the body. Now what happened? Now when you applied this force, the body is changed, correct? Its length became this much. So by how much has it increased? It has increased by a small amount, which is given over here, this one, correct? बरोबर है? This is said to be delta L. So this we call it as change in length. So this extra length that we have occurred is written as change in length. Okay? Hello?
Yes.
Okay. So we term it change in length. So here we say strain is change in dimension. So our case, what was change in dimension? Change in
Delta
dimension was
L.
change in length upon original length. Now remember, here there is no dimension to this particular thing, because if you are measuring the change in length, you are also measuring the original length in the same unit. So strain doesn't have any unit. Is this clear? Hello? Have you followed? Can I go to the next page?
Yes, sir.
Okay. Now here we look at within elastic limit, means as long as the body is elastic, the stress that we produce, that tend to produce strain. Stress is the cause, strain is the effect. So within elastic limit, stress is proportional to strain, and this is called Hooke's law. And the ratio of stress to strain is called modulus of elasticity. Okay. Remember, unit of dimensions of modulus of elasticity you will have to learn, because it's very important. Tell me, what is stress? Hello?
Force upon
Force
area.
upon area. So force upon area. And this is dimensionless, so it doesn't have any dimension, correct? So force is equal to what? L M L T raised to minus 2. How much is area? A raised to minus 2. Correct. So it will become M L raised to minus 1 T raised to minus 2. This is the dimension of modulus of elasticity, which you need to remember. It will come in the exam. Is it clear? Hello? Can I go to the next part?
8 seconds, sir.
Okay. Now we look at the different parts of it. Okay. So this is modulus of elasticity. Now we look at individual thing. Now see, like we started with the example, this is a rod that we have seen, and here we see that the original length, that is the blue color thing, was this much. We applied a force and we got a additional extension of this is called the extension, correct? So this part over here was the length, this was the delta L, correct? Now here the length is increasing, so this type of deformation is called tensile. Okay. So here what is the stress called? What is stress? Tell me. Your stress is equal to force upon area. And what will be our strain?
Delta L by L.
Yeah. Strain is equal to delta L by L. Sometimes in some book we write it as small l upon capital L. Now the Young's modulus is the modulus of elasticity for tensile stress. Young's modulus will be equal to what? It is written as Y, which will be equal to F divided by A, in turn will be divided by L, small l upon capital L. So you can write this as F into capital L into A into small l. Okay. Sometimes we want to find the extension. So using this formula we can also find the extension. Extension small l is equal to F into capital L divided by A into Young's modulus. Okay. Is this clear? And this type of deformation is called tensile deformation. Okay. Yeah, I have noted it. Can I go to the next four chapter?
Yes, sir.
Yeah. Okay. Now here we see a spherical vessel, and let us say that the original volume of the vessel is V. So we have original volume, which is capital V, and then we have applied force on all the sides like this. Some of the forces we have shown, some of the forces is to be imagined. Okay. Now the force is applied over an area, so force upon area in this case will turn out to be pressure. Okay. And it is applied on a bulk thing, so we can say that this is bulk stress. Bulk
Somebody.
stress. Now what will it produce? The strain will be change in volume. The strain will be equal to change in volume upon original volume. It will be negative because it is decreasing. So
Sir, could
here,
you email me
hello,
somebody?
hello.
Yes, sir.
So the bulk modulus in this case, the modulus of elasticity is called bulk modulus, and capital B will be equal to pressure divided by minus delta V by V. So we can say that it will be equal to PV upon delta V. Okay. Is this clear?
स्टार्टिंगला समजलं तो प्रेशर कसं मिळतं
फोर्स अपॉन एरिया काय होतो?
प्रेशर
हां, तर इथे व्हॉल्यूम आहे ना, इथे लेंथ आहे का तुझ्याकडे?
नाही
आता व्हॉल्यूम असल्यामुळे त्याला आपण प्रेशर घेतो. ठीक आहे. तसं पण प्रेशरचा आणि स्ट्रेसचा डायमेन्शन आणि युनिट सेमच आहे, न्यूटन पर मीटर स्क्वेअर. ओके. टेन्साईलमध्ये आपण त्याला एफ अपॉन ए घेतो. बल्क असेल तर वी टेक इट ॲज प्रेशर. डिड यू गेट इट? हॅलो, इज दिस डन?
येस सर
Okay. Now we go to the next part of it, and we look over here at shear stress, a different type of stress, and we call it as the shear stress. Okay. Shear means the shape changes. Okay. Okay. So here what we do is we take a cubical object. So here we have taken a cube. Okay. Fine. Now remember that this part of the cube, the bottom part is fixed. We have kept the bottom part fixed. This part is fixed, and we are applying force at the top surface. Okay. So we are applying a force over here, and area on which it is applying is this. So if you just talk about stress, then our stress will be the original F upon A, there will be no change in it. But if you notice the thing, the body will actually go this way. The upper one will move the most, and subsequently each layer will have a lesser and lesser change in shape, correct?
हा
Okay. आणि त्याची मॉडिफिकेशन, त्याची जे डिफॉर्मेशन होईल तो असा काहीतरी दिसेल आपल्याला, करेक्ट? हॅलो.
हा सर
ओके, ही अशी दिसेल आपल्याला, अँड दॅट्स वाय इट इज कॉल्ड शिअर स्ट्रेस. ओके. Now if
हा
you redraw this, we can say that our original shape was like this, and now what happened to the body? Its shape changed like this. Okay. So it underwent a change like in theta. So this was our length L, this was delta L. So you can say that delta L upon L will be equal to tan theta, and for small values we can take it as theta. So modulus of shear modulus, so your shear modulus, so shear modulus eta can be written as F upon A divided by delta L upon L. Now remember, here the area is the top port and the length is the vertical distance, and delta L is the one which is the maximum change in the upper area. Modifying this slightly from what we have learned, this will become A into either tan theta, or you can also write it as F upon A theta. Okay, is this clear?
येस सर
So we have learnt about tensile stress, bulk modulus and shear modulus. Okay. Fine. Can we go to the next part? Hello.
येस सर
Okay. Now here we look at something very interesting. To begin with, we take a body and we subject it to different stress and different strain, and we draw a graph of it. Okay. So till a certain amount of stress is learned, we get a straight line. Okay. So on the bottom we are applying what is called as a strain. It doesn't have a unit. On the y-axis we are writing stress, which is measured in Newton per meter square. Okay. Fine. Now till this point, what is happening? Our stress and strain are same. That is called point of proportionality. So if you remove the body will come back to its original shape. Correct?
हा
After the point P, the body undergoes a certain change. The graph actually becomes curvilinear. It becomes like this. Correct? Up to a point, let us say point E. This is called this is point of proportionality, this is point of elasticity. See, from P to E the body is elastic, but what happens to it? You will notice that a certain amount of deformity is conserved, correct? So P is point of proportionality. Up till point P, stress is exactly equal to strain. If you remove the body, it will come back to its original position. Between P and PQ, it has deformed, correct? So this particular portion that you see is the deformation that is retained by the body. Okay. Beyond this, the body starts expanding very quickly up till the point Y, which is called the yield point. Correct. Now here see, if you look carefully, your stress is hardly changed anything. Stress it is changed very little, but the strain that is there, it is changed a great deal. That means the body is undergoing a very rapid change. This is the portion when the body is plastic. Okay, at point Y the body has given up. Now it will curve downwards like this till the point E. Correct? Okay, this is called the break even point. So at this point the body actually disintegrates or it becomes brittle. Okay, also if you notice carefully what is happening here, your stress is actually decreasing, but in spite of that your strain is increasing. So between Y and B, even though your stress is decreasing, the strain continues to increase. Between E and Y, for a very small change in stress, there is a large amount of strain that is returned. Between P and E, you will notice that the body is elastic, it comes back to its original shape, but a small amount of deformation is there. And between O and P, it is completely proportional. Is this called? And this is called a stress strain graph. This is called a stress strain graph. Now remember, various bodies will have different graph. Correct? This is the graph of a steel wire. If you look at some other wires, it will have a different shape. Like for instance, if it is a plastic body, then you will notice that the body will start deforming right from the beginning itself. So its graph would look something like this. Correct? This is for a plastic body, like clay for instance. And if you look at a brittle body and you look at a stress strain graph, you will notice that it hardly undergoes any change and it suddenly breaks off. From here it will break. Correct? So this is for a elastic body like steel for instance. Example is steel. This is clay. Here also we have the graph of strain versus stress. Here also it is strain versus stress. Correct? This is a brittle body. Now there is another type of body that we actually call a elastomer. Okay, it is very interesting for bio students. All the cartilages in your body, the nose part, all of them are elastomers. Correct? And it shows you a very interesting graph. So if you look at the graph like this, this is your strain, and look at the shape of the graph. The shape of the graph is very different. The shape of the graph is, when you apply the stress, it undergoes like this, and when it strain is removed, it slowly turns out and comes like this. They both follow the different thing. The area under this graph will be equal to the energy stored during the cycle. Correct? This is for a elastomer. Did you understand this part? Hello? If you have noted, tell me, I will go to the next page. Hello?
Yes, sir.
Can I remove it?
Yes, sir.
Okay. Now we look at work done in a elastic process, correct? So to begin with, let us say that we have a elastic body and this is its original shape L, and we have extended it from here to here. This is our extension. So this extra part that you see over here, this part from here to here, is the extension that we produced, that is L. Okay, now we make it go through a small extension, extra extension dl. Correct? So the small amount of work that you did, that is dw, which will be stored at its elastic energy, will be equal to the force applied by you into dl. Correct? Now remember, In our case, force upon area divided by extension upon L is equal to Y, correct? And we can rewrite this by writing it as F into L upon A into small l is equal to Y. So what happens to your force? Your force is equal to Y into A into L divided by capital L, correct? Hello. Now, if you take this part and put it over here, then the small amount of work done in moving it by a small amount dA becomes Y into A into L divided by L into delta L, correct? Hello.
हाँ
Now, the total amount of work done or the total elastic energy stored in the body due to deformation will be the integration when there was no extension to when it was complete extension into dw. Now you notice carefully F, A and L will not undergo any change, so we will take them outside. So our Young's module is a constant, it will not change. The original area of the body will undergo no change. This will be Y. Inside the integration you will get 0 to Y L dl. Now from our simple integration of x, we know it is equal to x square by 2. So Y A L. Here you will get half and you will get L square, correct?
हाँ
Now reworking this, you can write this as Y into A upon L, correct? And then you can write this as small l and here another L, and you can write the half outside, correct? Hello. Now if you look carefully, this particular thing over here is nothing but the force itself, correct? So this part over here is force itself, this portion, and this is extension. So we can say that work done in an elastic process will be equal to half into the force applied into extension produced. So in simple verbal terms, we can say that elastic energy or work done will be equal to what? Will be equal to half into force into extension. Okay, is this clear?
yes sir.
So we now know the elastic energy in a substance, correct? All right. Now let us try to compute a very similar looking thing here. Okay, have you noted
हाँ
down? Can I go to the next?
yes sir.
Good. So we remember earlier what we have written. We have written that our work done or energy stored was equal to half into force into extension, correct? Now you divide this energy by volume, correct? So you will get energy per unit volume. You will get energy per unit volume, and that will be equal to what? Half into AL, and what will be the volume? Volume will be area into original length, correct? Now
हाँ
if you look carefully, you will get half. The next term is force upon area. What is it? Force upon area? It is stress, correct? And this is strain, isn't it? The second bracket is strain, the first bracket is stress, correct?
हाँ
So energy density, energy density, that means force per unit area, is given by what? Half stress into strain. Okay, it will be equal to half stress into strain. Is it clear? Hello. Now,
So,
remember what was y equal to? It is equal to stress upon strain, correct? So, what is stress will be equal to? Your stress could be written as y into strain, correct?
ah,
Y into strain, correct? On substituting, this will become half into y into strain the whole square. Similarly, your strain can be written as equal to stress upon y. So this whole thing can also be written as this, correct, into stress square upon y. Okay. Is this clear? Hello.
yes, sir.
So what all we did? First of all, we talked about mechanics of solid and we understood that solid have a special space. That means they have a definite shape, and that is because inside them the molecules are always held at fixed position. They are in equilibrium position, so the potential energy is zero, potential energy is minimum, and the force acting on them is zero. So if you change the position of the molecules, the shape of the body will undergo a change, and the molecules themselves will come together to produce a force trying to regain the original shape. So the force is internal, which we call it as stress. Okay, stress is force divided by area, and the change in shape is measured in terms of the change in shape depending upon the original shape, and we call it as strain. So we have substances which regain completely their original shape, we call them elastic substances. If they do not, we call them plastic, and if they disintegrate, we call them brittle. Then we look at the ratio of stress upon strain, we call it as modulus of elasticity. We'll have different modulus of elasticity depending upon the type of stress the body undergoes. Okay. Then we have Hooke's law, which says that as long as the body is elastic, or in technical term within elastic limit, stress is proportional to strain. Stress is the cause, strain is the effect. Then we had three type of deformation: tensile stress, bulk and shear stress. Correct. So we have
Ah,
Young's modulus, Bulk's modulus, and shear modulus, and we have expressions for them. Okay. Then we came down to the energy or work done in an elastic process. We knew that the work done or energy stored is half stress into strain, and energy density is what is on the board, that is equal to half stress into strain, or you may write it as half Young's modulus into strain, or half stress divided by Young's modulus. Okay, is it
yes,
clear?
yes, sir.
Hello. Now you go through all these things. This is a easy chapter. We can do most of the numericals. Tomorrow we will finish the numericals in this chapter, and again we will start with fluid. Okay.
Yes, sir.
Okay. Okay, then see you.
Yes, sir.